Welcome back. In lecture 43, we will look into link assignment, and link assignment module lecture is divided into two parts. So, we will start with part 1. So, the different concepts that will be covered, we will look into the background of link assignment, and then we will look into all or nothing traffic assignment, incremental traffic assignment, and finally capacity restraint traffic assignment. So, these are the three traffic assignment techniques that we will cover in this lecture. Other techniques will be covered in the next lecture. So, the process of assignment undertakes several steps to distribute traffic load along the links in a network. So, we have the steps, some of these steps we have already discussed, like for example, the step 1 is to identify a set of routes which might be considered attractive to the drivers, and for this we have learned about minimum tree, the shortest path algorithms which were engaged to determine which were the attractive routes in terms of cost or any other forms of impedance. So, first step was to determine what are the route choices individuals get, or rather vehicles have this route alternatives to traverse, and that is the first step to identify. So, in step 2, the job is to assign suitable proportions of the trip matrix to these routes or trees, and for that we require several assignment algorithms which distributes the flows across the links based on capacity and travel time. Now, what it means is we can take suitable proportions of the trip matrix. Why? Because if there is only one route, the entire total amount of trips for a particular interzonal trip volume would be assigned to a particular route. If there are multiple alternative routes, so there would be a certain proportion of the trips assigned to each of these particular routes. So, our job is to understand how do we divide this proportion, and for that we use these assignment algorithms, and that is what we will learn in this particular lecture. And finally, once these two steps are undertaken, that is, we have first determined which are the optional routes, then we have assigned the different determined interzonal volumes into these particular routes, and the third step is to what we do is we then iterate this pattern of assignment, and so that what happens whenever after each iterations there are adjustment to the total capacity, the travel time along the link as well as the capacity, and so with each iteration gradually we come to a point where there is an optimum solution, or we can also even say that some amount of equilibrium is established. So, once the ideal solution is attained, the iterative process is terminated, and this step is conducted over and above the two steps to search for convergence. So, first assignment technique is a deterministic one, and this is known as all or nothing assignment. This is the most simplest method. In this particular method, the trips from any origin zone to any destination zone are loaded onto a single minimum path cost between them. So, this algorithm, as you can understand, of course, we will discuss about the algorithm, but some assumptions about this particular algorithm. This assumes that there is no congestion effect, that is, link costs are fixed regardless of traffic volume. So, that means even though I am assigning the entire volume to one link, we are assuming that the link volume is the travel time along that link is going to be same, or the link, that means the link cost is going to be same, which does not depend on the traffic volume, which is not the case. And then all drivers consider the same attributes for route choice, and they perceive them in the same way. That means everybody feels that this route is the shortest one, and that means they will value it in the same way, which is again not the case. And then these assumptions might work in only that means that if their total demand is very less and we have a very high capacity network, then probably this will work, because we will not able to reach the final overall capacity. So, we will always have this uninterrupted flow, and this maximum speed would be there in the corridor. So, in that way we can assume that in a very sparse or uncongested network these assumptions might work. So, this actually helps us to determine a sort of a desert line effect. That means what would drivers do in absence of congestion, and this actually gives us an idea where to invest maybe. So, that is one way to think about it. And building blocks for other assignment techniques such as equilibrium or stochastic method actually starts from this particular technique. That means once we know of this technique, then automatically we can gradually modify it to in form of other techniques such as equilibrium or stochastic methods. So, the different steps in step 1 we compute the scheme trees via minimum path algorithm. So, we for every zone I to every zone destination zone j, we will estimate the minimum paths, and once we do the minimum path, we also develop a trip interchange matrix based on data collected from origin destination surveys and all, or in the it's from the maybe from the trip distribution part, and then develop a link interchange table, and finally some link volumes for each interchange utilizing that link to estimate total traffic volume. So, these are the basic steps. I will explain it to you using an example, and this is as you can understand, this is a little bit unrealistic since it ignores the fact that link travel time is a function of link volume, and when there is congestion, multiple paths are used to carry traffic, because automatically the travel time in one link goes up, so another link becomes more attractive, and so some people will go into the next link, and this happens continuously until there is equilibrium. So, in all or nothing assignment, let us see this particular example. So, we have 6 zonal centroids, 1, 2, 3, 4, 5, 6. Then travel times on the links are also given, which is over here, and we also have the total interzonal volumes, that is from 1 to 2 is 1000, 1 to 3 is 1100, and 1 to 4 is 400, and so on. All or nothing assignment method is used to determine the total trips for each link after all the trips from the following two-way trip table has been loaded onto the network. So, we will do that. So, first we have the trip interchange matrix, and we also have the link impedance data. Next, this, as you can see, this is the total of Pi of this total from number of trips starting from zone 1 is 4800, number of trips starting from zone 2 is 4050, and so onwards. And what we do is the next we develop the scheme trees via minimum path. So, we determine based on the impedance data for this particular network, we have already determined how to estimate the shortest path, and we can use any one of the algorithms, and for using that we have determined over here the shortest path between 1 to 2 is 1 to 2, that means this is the link, and then 1 to 3 is via 163. So, 163. So, 1 to 3 the shortest path is via this way, and then that means this has got two links, 1 to 6 and then 6 to 3, and then for 1 to 4 the path is via 1 to 4, the path is via 1634. So, this is the path from 1 to 4. So, over here we have got 3 links, 1 to 6, 6 to 3 and 3 to 4. So, in this way we get the different links, and once we have that, we now need to put in the link volumes into each one of these particular links. For example, when we have got 1 to 2, that means is there any other place where 1 to 2 is there? So, if I look into all this data, I do not see there is any other 1 to 2. So, that means 1 to 2 value is 1000. Let us look at 1 to 2. What is the value? So, 1 to 2 there are 1000 trips. So, 1 to 2 has not been repeated in any one of this particular the shortest path. So, that is why this 1000 trips is fully assigned to 1 to 2. Now, let us look at in 1 to 3, that means we have a shortest path which is 163. So, 1 to 6 and 6 to 3 are the two links. So, let us look at 1 to 6. 1 to 6 appears over here, 1 to 6 appears over in 1, this is from 1 to 3. So, 1 to 6 again appears over here, 1 to 6 again appears here, 1 to 6 again appears here. Then we do not see any more 1 to 6. So, 1 to 6 must be the addition of 1, 2, 3, 4. So, this 4 traffic volumes, because these 4 traffic volumes would be loaded onto 1 to 6 eventually during their shortest during the movement along the shortest path. So let's look at 1 to 3, that means 1100 plus 400 plus 1000 plus 1300. So that comes to around 1000, 2300, 2700 and 3800. So 1 to 6 is 3800. So that is right. So in this way we will load the different traffic volumes into the links that falls on its shortest path, and eventually we will get the total amount of volume in each of this link, and then we can also see that which of these volumes exceed capacity using V by C ratios, and we may propose expansion of certain links, or we may propose some other measures to reduce volume in that particular link, and so on. So the minimum path table is constructed and trips are assigned to each link based on the trip matrix. The final solution is given as we have just estimated the final solution. So next we look into another technique which is called incremental assignment. This is also a deterministic technique. Now what this technique assumes is each trip maker chooses a path so as to minimize his or her travel time. This is basically following Waldrop's, we have already discussed Waldrop's equilibrium. So this is following Waldrop's first equilibrium. So each trip maker chooses a path so as to minimize his or her travel time. So travel time on a link varies with the flow on that particular link. So that is also what we have learned. That means if the flow increases, the travel time will also increase. So the ideal way to solve this particular problem is the traffic volume is assigned single trip at a time on the road network, assuming that the travel time on links during that assignment process remains constant, and after that we update the travel time considering the current traffic volume in that particular link. So that means once for the entire whatever in the previous step, whatever you have done, you are assigning the entire trips entire interchange volume into a particular link if it was going along a particular shortest path and if that link was in the shortest path. But over here we ideally we should have done it one trip at a time for the entire process, and then update the travel time in that link, because one, there is increase in the traffic volume, and then if it doesn't exceed capacity, then it will more or less remain same. So in that way, but at one point you will see some links will exceed capacity, then the traffic volume starts to increase, and then what happens, the impedance increases and the shortest path may change. So if the shortest path changes, that means the entire traffic volume would be loaded into another particular link. So that is what actually helps us to determine that how traffic volume would be divided among different paths or links. So that is the ideal way, but actually it is not possible, because if I do it one trip at a time, it will take a long time to execute the process, and as well as it is not required. So instead what we do is we do something called an incremental assignment technique, where we divide the total amount of trips of each particular link into a few smaller parts, and then assigning each part with a constant link travel time, and then we update the link travel time, and then we assign the next part and so on. So this overcomes the shortcoming of all or nothing assignment technique by incrementally assigning the entire trip distribution matrix and updating the link travel times with flow. So we are able to update the link travel times after certain intervals. It does not have any behavioral basis and do not mirror the root choice behavior of humans. True. That means it doesn't incorporate, again it's a deterministic method. We are assigning a particular traffic volume entirely into a particular shortest path. So there is no route choice option. So because of this assignment process, there is change in the travel time. That's why the shortest path changes. But as such, there is no behavioral basis that has been considered. That means humans or the individuals, they haven't given a route choice based on certain other the characteristics that they would have evaluated. So this is a computational technique of traffic assignment. So this has got no behavioral basis, but at the same time, this is a technique which actually assigns traffic to different paths instead of just a single path in all or nothing assignment. So as we are discussing, like the traffic volume increases, the link travel time actually decreases. So volume delay relationship, or which is also known as the cost flow relationship, this we have learned earlier. And average travel speed decreases with increased flow or volume, and average travel time increases as the volume to capacity ratio on a link increases. So this is this over here you can see that when volume by capacity ratio actually increases, that means the volume first and then the final travel time or the free flow travel time also actually increases. So final travel time divided by free flow travel time, that also increases. So that means when the ratio is 1, so this is the when volume is equal to capacity, this is the case where we also find final travel time divided by free flow time is little bit above 1. And then if when it is 2, we can see that final travel time is almost 3 times than the actual free flow travel time. So that is what actually this graph shows. And over here, this is the BPR equation, this is the BPR curves. So we have learned about the BPR, Bureau of Public Roads, that function where we were estimating the travel time of a link based on volume by capacity and the previous travel time, the free flow time. So this was the BPR equation for equation. So we had got alpha and beta over here, and alpha value was 0.15 last time, but now BPR equation we are considering freeways and non-freeways, and there these parameters have changed, coefficients have changed, and 0.15 has become 0.2 in case of freeways, and for non-freeways it has become 0.05. So alpha and beta values can be calibrated for various link types and assumed LOS for capacity. That means for different freeways or non-freeways, or these are American terms, we would have different LOS level of service for this particular capacities and all. Based on that, these parameters change. And travel time is a power function of the ratio of volume to capacity. This we have already learned. And for LOS E capacity, that means LOS E means very lot of volume compared to capacity. That means many more times of volume. So in that case, what happens that alpha is closer to 1. So when alpha is closer to 1 and beta is closer to 4, and V by C is equal to 1, then we see that travel time becomes 2 times. So here we are seeing 3 times. So here we can say that travel time becomes 2 times of free flow time. And if V by C equal to 0, then travel time is equal to T0. So that is what we can see. So these are the these are the curves for standard BPR. This is the standard BPR, whereas these are modified curves for freeways and modified curves for non-freeways. So here we have speed and then we have volume. So that means when volume increases, automatically speed will gradually come down. So initially speed remains same, but then suddenly there is a very drastic reduction, and then again it becomes more or less stable. So this kind of S curve is seen in many cumulative distributions as well. So this kind of curve is what we see. So initial part the change is less, then suddenly there is huge amount of change in the middle. So in addition to the BPR equation, we can use the Davidson model as well to determine the final link, the travel time in a particular link. And here this could so Davidson model can be also used to determine the link cost function, where TQ equal to T0. T0 is the free flow time, and where and over here on this side we have 1 minus tau into Q by Q max. So Q is flow divided by the maximum flow in this particular in this particular link, or and then divided by 1 minus Q by Q max. So we need to understand what is Q max, and also this tau value also we need to know. So tau is basically called the LOS parameter, and it takes the value of 0.1 to 0.2 for freeways, 0.4 to 0.6 for urban arterials, 1 to 1.5 for collector roads. So these are again empirically estimated values based on wherever this model was calibrated. So Q max can be estimated with the help of another model, which is Greenshield's model, and the relation between flow and density is given in the model as this is the relationship between flow and density. So Q is the flow at density k, and Vf is the free flow and free flow speed, and Kj is the jam density or the congestion density. So this is the particular formula that is being used. So as you can understand, now if I want to find Q max, that means I have to find that at what value Q becomes max. So for that we take a derivative, as we know that we want to maximize the value. We need to determine at what value it becomes, assumes the maximum value. So we can take a derivative of this particular function and can equate it with 0. So that is a standard way to find the max value. So we derive max flow, we differentiate Q with respect to K, and then also we equate it to that 0. That means when we say dq by dk is equal to 0. So what it means is when we take dq by dk, it actually becomes this equation becomes Vf minus Vf by Kj into 2k equal to 0, and which actually comes to k equal to k by 2. Now, if I replace k equal to k by 2 in this particular equation, the same equation where q has become now q max because we are replacing k by kj by 2, and then we get to the point when we can equate it and we get this particular formula where q max equal to kj. Kj is the density at congestion into Vf, this free flow speed, divided by 4. So that means this is the formula that we can directly use, and this actually will give us Q max, which we can put in this particular equation, and based on that and the actual flow in that particular corridor, we can determine, and tau, of course, what kind of corridor it is, we can determine how the impedance travel time cost or the impedance will actually increase in this particular corridor. So this is another alternative equation you can also use to determine link travel time. So now how do we do the incremental assignment? Well, this steps looks complicated, but actually it's very simple. We divide the entire trip distribution matrix or the origin destination matrix into n smaller part. That means we divide into n smaller part. We can divide it equally, but in most cases we can divide it at the beginning. It's a little bit larger chunk. Then we can have equal values, or we can gradually reduce it, because what happens, as you have seen from the BPR equation, the speed reduction is not drastic. So it remains same till the capacity starts really increasing, and then gradually it dips. So for the first part we can take a larger chunk, and then we can make a larger size of the we can divide a larger piece of this travel interzonal volume at the beginning. So we can divide it into n smaller parts, and then the sum of all these matrices should be equal to the actual trip distribution matrix. That is understood. And first we set counter equal to m equal to 1, and we set this variable x a m minus 1, that is for this first iteration. That's why we are using this kind of terminology. For set this value volume is equal to 0, that means this is the traffic volume assigned to a particular link. So this value is set at 0 for all A, and also note in the following Tijm refers to the number of trips from I to j as per the mth part matrix. So whichever matrix we are using, so this is the first that particular part's traffic volume, that is what we are referring to. So we first set the VA volume for all links, assuming that tau A for this particular iteration, we will set the all link travel times and assign the trips of mth part matrix using all or nothing assignment technique. So and then store the link volumes obtained from all or nothing technique as VA, and then what we do. So what it basically means is we assign the entire first chunk of the trips that we have actually divided, and that into the network using the travel times that is there, and then we will update the total link volume, and that update the link volume is xam equal to xam minus 1 at the beginning plus VA. So initially it was 0, so 0 plus VA. So in the next one it would be VA plus the new value that is being added. So in this way we will gradually keep on adding it, and at the same time keep on updating the travel time as well. That means that impedance value will gradually increase. So we will continue till m is equal to n. That means we reach all the smaller parts have been included or assigned into the network. So again, let's see this with an example. So over here we have got the OD matrices A to B, A to A, A to B, A to C, and similarly B to A, B to B, B to C. So you see A to B and B to A is more or less same. So both is assigned onto the network together. And for the network shown in the above figure, the trip distribution matrix given in the table determines the link flows using, we will first determine using incremental assignment technique. Now the link travel times tau A x A are given by, we are using the BPR equation. So tau A x A equal to Ka plus 0.15 and this xa by Ba. So basically the form that we used in the BPR equation initially. So the link, for the link number, for each link number, the Ka value and the Ba value for a particular link are mentioned. So Ka was the initial travel time and Ba was the capacity, and and the link number is also mentioned for a particular link. So alpha, beta, gamma. So 1, 10 and 200. So 1 is the link number, 10 is the travel impedance and 200 is the capacity. So that means, so this is this Ba. So using this data, as we can see, there is only one way to go from A to B. So there is 10. We can always go from B to C and then A, but obviously this is 10 plus 15. But eventually, if I keep on loading values over here, we may find that another route has become faster. But over here, directly in B to C, there is, there are two options to go. B to C, we can actually three options. B to C, we can go along this route, or B to C, we can go along directly, or we can go to B to C like this. So this way it is 25 minutes, directly it is 10 minutes, this is 20 minutes. This is initially when there is no loading on this network. So once we start loading it, these values will change. So we divide the entire matrix into in the ratio 40 is to 30 is to 20 is to 10. So I was telling you initial one is big, then gradually we can taper it off, or we can even make equal parts. So this is how we have divided the matrix. So this is the 40% of the total trip volume, this is 30%, 20% and 10%. So then we said V1, all the values are 0 as per our algorithm that I have given, and initially all volumes are 0, and we take the travel times impedance as the ones that we have given. So travel time for the different links are also there. So this is 10 minutes for link number 1, for link 2 it is 20 minutes, link 3 it is 20 minutes, and link 4 it is 15 minutes. And all or nothing assignment is adopted, and we actually get the following values for Va. So V1 is equal to A to B plus B to A. So we are adding both directions together. So that comes to 200. V2 is B to C plus C to B, that is 320. V3 is equal to 0, and V4 equal to A to C and C to A. Now V3 is equal to 0 means we are not assigning any traffic or volume on this particular link, because it is more than this one. So So once we have done that, so the next thing is to update the travel time also, update the volumes. So using XA0 and VA, the following quantities are obtained. So we add with the previous value of the load that was there, volume, we add the new volume that we estimated. So it remains as 200, 320, and then again 0 and 120. So these are the link volumes. And then because it is we have not reached the last part, which is we have 4 divisions. So we divided the matrix into 4 parts. So n is equal to 4, m now is 1. So we have to continue this step, and for that we updated the travel time values. So like over here, so we have to update the travel time values based on this particular volumes, and then again we will repeat the steps. So after completion of iteration m equal to 4, so after 4 times, the trip assigned to the links are reported as, so you will find that if you can work it on your own, and you will find that the total link volumes will become 450, 560, 290 and 350. So you see that there is some amount, even though X3 is initially having higher travel time compared to the other one. So in that case, if there was no volume assigned in all or nothing assignment, there would have been no volume assigned, but because we are doing incremental assignment, there is volume eventually get assigned, because the travel time of the alternative route gradually becomes higher. So that is why we see some volume in X3 as well. So then we go into the capacity restraint assignment. Now, so this is a technique which actually approximate the equilibrium method, or we will discuss equilibrium method in the next lecture. But we have already discussed in Wardrop's first principle that gradually equilibrium is established when everybody chooses the shortest path. So it cannot be done at one go, and either we can assign one card at a time, update the volumes, in that way it can happen. So over here, when we consider capacity restraint assignment, it's a approximation of achieving equilibrium. So it's an iterative scheme, and a repetitive all or nothing assignment is done, in which all travel times resulting from the previous assignment are used in the current iteration. And this captures the equilibrium nature of the traffic assignment problem to some extent, and the algorithm may not converge. That means every time I do all for nothing assignment, I don't divide the entire traffic volume into small parts. I assign the entire traffic volume into one link using all for nothing assignment. I get the travel times. Using the travel time, I update the link travel time, and we again find the shortest path. And once we do that, again we do the assignment, and we keep on doing that. So there may be no convergence. So there at never convergence basically means there is no change in the travel times further after any more iteration. So there have to be some other methods to make this algorithm stop or to come to a particular result. We use a technique called smoothing and averaging. So where what we do is temporary link travel time is estimated, that we estimate over different iterations is averaged together, and the travel time used in the last iteration is averaged together with the travel time used in the last iteration to obtain link travel time for the current iteration. So that means instead of assigning the existing the estimated travel time in the last iteration directly for all or nothing assignment, what we do is we take a composite measure where we consider average of all the iterations earlier, because you see travel time drastically, whenever you load a particular link, travel time drastically increases, automatically the entire volume goes into the next one. And again, you know, the traffic volume will once jump from this jump between two links, right? So it will keep on jumping each other. So that means there would be no end to it. So instead, if we take average of these volumes over all the iterations plus some amount of weightage given to the value of travel time that came in the last iteration, and using that we can iterate for the next step. So in that way we can actually smooth the process, and we can average the process, and this partially overcomes the problem of allocating too much traffic to low capacity links. That actually that was the problem I was telling you, that already, you know, traffic volume is jumping from one link to another in each iteration, and sometimes in some low capacity links, you know, traffic it happens like that, and equal weight is given to each auxiliary flow. So we start with TA0. So this is time. We estimate volume x and choose the route with all or nothing assignment. We calculate value of TA, the new time, and calculate the new value of TAN for the next iteration is from 0.75 of TAN minus 1, that is the previous value, plus 0.25 into tau Na. So this is the estimated value that we have just now. So that means we take 75% of the average and 0.25 of the last iteration value. So we can again repeat the steps, and we will keep on doing that. and calculate with several iterations. We can do it for any number of iterations. Then average of flow of traffic in each, then we calculate the average of both flow and time for all the iterations, and that is our result. So we take the average value. So first we smooth it and then we average it out. So what is the stopping rule? The stopping rule is number of fixed iterations or no change in link travel cost over 2 successive iterations. So that means the convergence is more or less being achieved, or it's a fixed number of iterations, and this algorithm may not converge to equilibrium solution in spite of these changes. So that also may happen. So let's see an example. We have 3 links from between O and D, link 1, link 2, link 3. So we have impedance of these 3 links 10, 20 and 25, and flow capacity is also given 2, 4 and 3. So vehicles per unit time. Now total flow, as you can understand, there is 10 units. So that means 10 vehicles go from O to D, and we divide it between these 3 volumes. So consider the figure and the table provided. So what we do is we use the BPR equation and we determine that T1 values, T2 values and T3 values. So over here you can see that this is we are using this impedance amount of 10, 20 and 25, and this is the formula that we use, and over here it is the capacity is 2, 4, 3. So initially it is 10 minutes is the least one, so we will assign all traffic to link number 10. So once that is done, we will update the link number 1, and once we do that, then we update the travel time units, and we may find that this travel time has become 20. So in that case we can, or 24. So in that case we can assign this to this one. So in this way it will keep on going. Let's see the results. So over here we initialize. So the entire traffic volume T1 is 10, T2 is 20, T3 is 25. So the entire volume is assigned to link 1. So we update, T1 becomes 947, T2 is remains 20, T3 is 25. So that means this is the lowest one. So we assign, then we then smooth we take the averaging smoothing process where T1 becomes 244 using the formula that I have shown, T2 remains 20, T3 is 25, and loading is again the entire loading is on that link number 2, and then we again smooth it. So this becomes 186, this becomes 49, this remains 25. So next time we will assign it over here. So this keeps on going, and eventually after suppose 3 iterations we stop, then we find the results by averaging all the values. So we find x1 is 2.5, x2 is 5 and x3 is 2.5, and that and travel time is 142, T2 is 42 and T3 is 26.8. So this is a capacity restraint assignment, and we see now the link volume is assigned between all the different links, all the different paths you can say. So this is the references you can study. So to conclude, in this particular lecture we have covered 3 assignment techniques, and while all or nothing assignment technique itself do not aligns to usual equilibrium principles, minor modification to its application in form of incremental assignment and capacity restraint assignment captures the equilibrium nature of traffic assignment to some extent. Thank you.